for a long time about this research station. I'm very happy to be here for the first time. And the other thing which I should point out is that there's sort of an unlikely event. I mean, there are 4 from 3 authors of this paper are actually sitting here in the audience. I mean, so that's sort of extremely unusual. Sitting here in the back. Okay, now the topic is a specific problem about the design equation, and I realized that it's a somewhat diverse audience, and of course some of you are experts, but other ones don't even know what the equation is. And so maybe it's another sort of beautiful example of non-equilibrium statistical physics. So maybe on the blackboard I will give you sort of a short introduction to what this KPZ equation is. And first we look at the equation itself.
Maybe click on your slide. If you click on your slide.
To add it to the, like the mark asks you if.
But it was working earlier.
It was working. But it's not. It was not in the slideshow, right?
Yeah. How do you? Do you know how to do that? I'm not. Can you go back to the full screen?
Okay, very good. So it's stochastic PDE. I mean, so. So it's a stochastic PDE. I mean, here it's written. It's in terms of a height function. And before sort of going through the few equations which I have, let me explain. I mean, where this actually comes from. And I have to break the symmetry somehow. I mean, whether there are more people sitting on this side or the other side. Okay, so the background is extremely simple. And I will explain it in terms of how the experiment is actually done. That's the Takeuchi experiments, which are sort of, sort of very well known in the community. So what you look at is you look at 2D stochastic icing. And so here's your lattice, let's say, this way. Okay, and you sort of put a domain wall state, which is sort of 45. I mean, so 45 degree, maybe like this. Okay, and so here you put initially all minus, and here you put initially all plus, and the dynamics is simply spin-flick dynamics, but I do this at very low temperatures. Okay, and so what happens at very low temperatures is that when you look at your free energy, I mean, and because I put the external field, I mean, this state will be sort of. I mean, so here's the plus state and here's the minus state. So I will have a metastable minus state and the stable plus state. So this is the free energy. Okay, and so you see what's happening is that this state down here at very low temperature will be basically the time stationary, and so will be the minus state. But at the interface, I can sort of have quick motions because it's very easy for the plus spin to be. I mean, here I have pluses and then the minus spin to flip to plus. I mean, that's a sort of fast process. And what this equation describes for you is, in this sort of tilted coordinate system, this would be the x of my continuum approximation. Up here. Okay. So here I have this continuum equation. So the x is this coordinate, and in this direction, I mean, you will see some height function. So this is the function h. Okay, and so if you look at the time evolution of this function, then there are sort of 3 terms over here. So that's intrinsic stiffness, because I mean this interface has an intrinsic stiffness, and that's sort of modeled by this Laplacian term. Then there's noise. I mean, that's obvious because you know, each one of these events is random, and so I have a noise sitting over here, and you know, it's random everywhere, because as the interface sort of progresses, it will see sort of, you know, different spins, and therefore it will see different noise. So here I put space-time wide noise, so it depends on x and t. It's correlated and normalized to 1. And this one is maybe sort of the most important term, is that this describes the fact that the growth velocity is sort of a nonlinear function of the slope. I mean, you know, if I tilt this surface a little bit like this, I mean, so this was the original, let's say, flat one, and then I tilt it a little bit, then it will have a different growth velocity. And this growth velocity, to lowest order approximation, well, there's a 1, but to lowest order approximation, it's sort of described by the second, I mean, by the square of the gradients, or by the square of the slope. Okay, so this is the equation, and now you want to sort of, you know, it's a standard sort of evolution of field theory, if you want, so in 1+1 dimension, and you somehow want to understand properties of this equation. And one thing which you realize is that that there's sort of a scaling property in this equation. And no, maybe I should say a few words about the first item. I mean, so of course I can put everywhere coefficients, you know, I can put sort of a strength factor over here and then over here. But you realize when you do those simple sort of v-scalings, that you can put all the, there's something not working here. Any help? Or we just have to hope that my machine is understanding this.
Okay. It's like it might be the energy saving mode or something like this.
We can plug in the charger.
So it's not
the charger. You can.
Okay, so you see the simple scaling. I mean, if you look at this equation at very long times, then you know, then basically you have to put it into the equation, and then you see that this term is actually very small, and this is sort of dominating the one. And if you see, you know, the way if I sort of fix the prefect of under v scaling equal to 1, I mean, then you discover that this 1 to 3 scaling. You know, if I want to say have sort of a long time natural limit, and the natural quantities is that their h is of order t to the 1/3, that's the height field, and the lateral coordinate, and that's x. I mean, so this one is the x here, and this one is the height. Has to go like t to the 2/3, and of course time goes like time. Okay, and then the other thing which you observe is that for this equation, it's a nonlinear equation, but you can actually compute what is the steady state. And you discover that for the equation, for the, you know, the height is sort of something which is increasing. It's like a bounding motion, so it will not be really stationary. But what is stationary? The stationary object is actually the gradient of the height. And so the natural thing to look at, or at least sort of, you know, the object, the observable, which I want to look at during this talk, is the gradient of the height field. I mean, so here you see the correlation of the height field, the gradient at 0, and the gradient is space-time xt, and I do the average over the steady state. The steady state is, as I said, it's spatial, mean zero spatial white noise. That you can check directly from this equation. Okay?
So this average is over noise. The average is over noise.
The average as well, it's a double average, right? I mean, first of all, an average with respect to the initial conditions, which is space-wise noise, and then, of course, it's the average over the noise. Okay. Right? I mean, so the usual two-point function which you sort of would compute in other field theories, right? So it's stationary. I'm looking here. Of course, you could also look at other situations, but for the whole talk, I will be looking at the stationary situation. I mean, it's in space stationary and in time stationary. All right, and well, then there's a remark that there's sort of a single universality class. I mean, that was the title of the talk, which I didn't even mention, but anyway, I mean, so you told the title, okay. So I want to investigate sort of universality classes, and here, you know, there's a simple, there's a single universality class. I mean, you know, I have this lambda, and this lambda somehow, you know, appears down here in the v-scaling, and therefore, you know, up to, you know, trivial v-scaling of the scaling function, I will see always the same thing.
So where are the parameters of the noise in this 2.5 where does noise appear in the two-point function?
Well, the noise doesn't, well, I mean, the H is a random function.
No, in the right-hand side.
On the right-hand side, well, I take the average, and then you see, this bracket means that I take average over the noise. And so I'm saying that after I've done the average, I see some function depending on X and T. And now what I'm saying is that for very long times, it will have a scaling form, namely that, it's not separately a function of X and T, but it's only a function of X over T to the 2/3.
So there must be some assumption about the form of the noise that
White noise.
White noise, it's white noise, space-time, white noise.
White noise, Gaussian.
White noise, space-time, Gaussian, white noise, space-time.
Non-Gaussian will give corrections.
It's a nonlinear equation, but the noise is, very simple. It's just random, maximally random in X and T. Now, is that fair enough, or you want to write me for you the covariance function?
No, it's okay.
It's okay? Okay. All right. But there's a double average, it's also that the initial conditions are average, right? All right. Now, those people who sort of are expert in these kind of things, should sort of worry a little bit, because you see, it's sort of, we get this exponent 2/3 in some sense by naive power counting. But, we have an exact solution. At some point, we discovered that, you can actually figure out what this scaling function is. So there's an explicit formula, and then, there's sort of no doubt that, this exponent 2/3 is sort of the correct exponent. But, this might not be true in general, but we will see. Okay, and so now, this is something sort of like I don't know. Many years back, at least sort of at various stages, but I certainly don't want to repeat this. I just want to say that sort of the more recent problem with which sort of I would like to explain during this talk is to sort of, if you want, sort of a trivial extension of this equation, right? Sort of minimal. You see, when you think about extension, then you think immediately maybe instead of, I have one space dimension here, right? This you can see in the picture. You can think of the same equation, let's say in 2 space dimension. But that's a different story. So I want to do something extremely simple. Namely, all what I want to do is I want to sort of take 2 components, right? Rather than having a scalar field, I take 2. Okay. It couldn't be more simple than that. Okay, and so now I'm writing down for you sort of explicitly sort of, this equation in 2 components. Of course, now you have many more coefficients appearing. And I've picked sort of a very specific choice of the coefficients. So, when you look at this first equation, then of course this one is always the same. This is white noise for the one component, and this is white noise for the second component. They're independent, these noises. They're not moving in the same field. Okay, so I have this one. I have the stiffness term. That's of course also the same as before. I put the one over here. Again, you could put a factor, but then you can shift it somewhere else. And now I choose sort of a very particular nonlinearity. And one is sort of, the product of the 2 gradients. Before we had the dxh squared, right? So maybe I should remind you of this. The standard nonlinearity in the KPZ equation was this term here, right? And so here you see now a coupling between the two components. And here you see another factor. So here's the square of the one component, the square of the 2 component, and then you have sort of x and y, which I put in red, so that it's not a variable. It's just a control parameter in this equation, right? It's the lambda in the first slide, and now I have 2.
So sorry, x is not space coordinate.
This x. No. This is supposed to be capital X, and it's a control parameter.
Okay. So you have to be a bit careful.
It's like the lambda in the first case. Here for some historic reason, it's called X and Y, and so this goes back to Kadar and other literature. So anyway, okay. So I want to sort of okay. So let me make first two remarks.
Can I check? Could I check?
Question? Yes.
Does the control parameter y just multiply the first nonlinear term?
Okay. No. It's just as written. It just multiplies this term.
Okay.
Just as written, okay, yeah. Okay. There might be printing errors later on, but I mean, for this one I was careful. All right, so I want to point out two things. I mean, you see, first of all, when you write down the equation, you know, why did I leave out the linear terms? Right? I mean, this is sort of a somewhat special situation, but if I add here linear terms, I mean, this is something which was sort of studied sort of like 15 years ago in great detail. And then something very simple happens, and I just want to sort of explain you the phenomena that, and then sort of make clear why we are looking at sort of something sort of slightly more complicated. What happens is that if so again, I start with sort of my let's say thermal equilibrium state. Everything is uncorrelated, and I put sort of, you know, a little bit of extra noise into this equation, right? I mean, you know, I just sort of put one of the fields, you know, I just make a local perturbation. And then you wonder how this local perturbation is propagating in time. And what you discover is that if you have these two components, that you will have two peaks which are moving out. I mean, that's just sort of because, you know, when I put this, I mean, that's just a solution of the linear equation, and that dominates everything. Now you see these two peaks have different velocities, and they're separating in time. Once they're separating in time, I mean, then you might imagine, you know, that this peak actually can be well described by the one component system. And also the other could be also well described by the one component. That's true, modulo some important details, but it's really true. And therefore, this is sort of what I would call a trivial case, right? It can be, you know, the behavior of the solution of the system can be understood in terms of the single component case. Now here, you know,
like question, can the faster one originate to the left?
Well, they could also, well, I mean, I just plotted this. I mean, yeah, one could move to the right and one to the left, but the main point is that it will have different velocities, right? I mean, sort of which way I put the velocities is sort of totally
okay.
But sorry, I mean, in higher dimensions where things are much simpler, you know, hydrodynamics in higher dimensions, fluctuations are small. But even there, these types of arguments don't work. You know, shear modes affect sound modes. Sound modes
well, I
affect
don't know.
modes.
I mean, the higher dimension is sort of beyond this talk. I mean, so
no, but I meant to give a simpler example where fluctuations are suppressed. Let's say just, you know, hydrodynamics in higher dimensions.
Oh, hydrodynamics higher dimension.
Yeah,
well,
so
no, but then you know, I will have the whole rotational symmetry, right? I mean, so it will not be just simple peaks. I mean, it will be something.
So your argument does rely crucially on.
Yeah, no. I think I'm really working very specifically for that case. Yeah. Okay, so so here I want to point out, I mean, that, you know, the two modes are actually strongly interacting because, I mean, they have the same velocity. Well, you know, by fiat, I put this velocity equal to 0, and so they're sitting on top of each other. And there's no reason why I should expect that, you know, just the results which you had for the single component case actually can also apply to this case, right? Okay, so this is why I'm looking here at something sort of. Now, why I'm actually looking, well, there's sort of three sort of earlier work which I want to point out, and one of them is by Erdash Kadar, you know, many years back. I mean, he was looking actually sort of like a stretched polymer sitting in a fluid, and you know, what are the H1 and the H2 are sort of the, you know, the polymer is like this stretched, and then you have sort of two transversal degrees of freedom, and this is sort of what is described by this equation, right? So, but then, okay, then Jacobo, somewhere sitting over here, I mean, he sort of studied a completely different problem, which, you know, has been very popular, namely the fact that, you know, this kind of KPZ physics you also find at the isotropic point of the Heisenberg spin chain. It's a chain, I mean, so it's in one dimension. And then he sort of devised sort of an approximate theory for that object, and then he came up, you know, of an equation basically of this type. I mean, so that's another. And then if you want to understand the phenomenon, of course, you have to analyze that equation, and so, you know, that's very closely connected. And then there's another work which I like personally very much because it sort of proposes a somewhat different and somewhat more direct physical realization. So this is sort of a problem sort of coming from nonlinear optics, actually. And in nonlinear optics, you can manufacture the system in such a way. You see, it's still one dimension, so it's sort of like a channel. But you can sort of get a sort of, you know, what would be the analog of sort of a Bose-Einstein condensate. I mean, it's not strictly correct because we are still in one dimension, but low temperature sort of, at least for short times, seems to be a rather good description. Now, if you can make, a single condensate, I mean, you can just put two channels, and then you have two condensates parallel to each other. And then, of course, when you look at since they have sort of quite a bit of freedom of how to do the interaction, they can also induce an interaction between these two condensates. Okay? And now you say, okay, physically it's clear that, whatever equation I'm going to write down should be invariant under the exchange of the two components. And so you require, sort of a general equation of this type, or, with a general quadratic nonlinearity, and you require, that it should be invariant under the switch between H1 and H2. And then lo and behold, I mean, after you have done sort of the analysis, you again sort of come back to this equation. And what I didn't display here, that there's sort of a third parameter which sort of enters up to here, which is sort of not so important. And for what I'm going to tell you, I put it always equal to 1. Anyway, so these are the motivations why we want to study these equations.
So just to clarify, so on general grounds, if you assume, 1-to-2 symmetry and x to minus x symmetry, you would also write down, cross term, in the second equation, you would also write down.
Yeah, that's right. I mean, you could see, I have three, and I have h1 squared, h1, h2, and h2 squared as the two terms which I'm writing down.
But you don't write them down because there is some filter definition?
No, I could write them down, but then I have a larger control parameter space, and then I don't know what I'm doing, right? I mean, and I'm just trying to say that if I impose this, in the case of Weinberger, if I impose this natural symmetry under exchange, I mean, then, the sort of the equation, the number of control parameters in the equation simply becomes smaller.
But these are not the most general equations that we
No, it's not the most general equation. No, I'm looking at the specific one.
Is it allowed to do so? Like not writing down
if you assume that you have this physical, that it's symmetric under interchange. In the case of Quadrat, it comes from analyzing this stretched polymer which is sitting in the fluid. I mean, you have to look at the particular physics, right?
No, I understand that. I'm just saying that these equations at the very top, these are not the most general equations that are symmetric under this interchange.
No. I mean, under this condition, they are the most general equation if you add another parameter which is sitting up here in the first row, which I didn't display. Okay, so now let's see how we do. Okay. All right. So now. Of course, there are two things which one would like to know. I mean, one of them is, what is the dynamic scaling exponent? And the other question is, assuming that there is one, or maybe computing possibly, the question would be, what are actually the universality classes? You see, for one component, so we had sort of like, just a single control parameter, and then everyone was there in the single, it was just one single universality class. But here we have now a somewhat more complicated issue, and of course it's not completely clear. Maybe that's just, what is actually are the universality classes? I'm defining in a second what I actually formally mean by universality class. But this is sort of what I'm after. I mean, there are two problems which are somewhat separate. And I'm fixing on the issue of what are the universality classes. Okay, and so now when you look at this equation, then you see already one difficulty that, and this is actually a very general difficulty for this sort of non-equilibrium, sort of stochastic modeling in non-equilibrium statistical mechanics. That we can write down the stochastic equation, but we do not know what the steady state is. Okay, I mean there's just it doesn't satisfy detailed balance, and therefore you have no sort of simple tool to actually write down what the steady state is. Now we did numerical simulation, and very strongly suggest that if I so maybe I should go let's say. So if I sort of put here some x and y, let's say for that argument I have to require that both of them are strictly positive. And then, we did some numerical simulation, and it's sort of, very strongly suggested by this stochastic equation that by the numerical simulation that when I look at the steady state, it actually still has a finite correlation length. I mean, this will play a somewhat important role later on, but let me just sort of go through this a little bit, sort of more step by step. I mean, so the first thing I look at the static correlator. This is now, of course, a 2x2 matrix. Now we have a symmetry. I mean, if I put phi1 to minus phi1, then stochastically it will be exactly the same. Therefore, the off-diagonal elements of this correlator are actually disappearing. So, I only have the phi1 and the phi2 and the same for the dynamic correlator. It's only the diagonal terms which disappear, and the off-diagonal terms are strictly zero. You can verify this also when you run the simulation. I mean, you see this extremely well. Okay, so that simplifies a little bit, because instead of 3 parameters or sort of a 2x2 matrix, I can look at the diagonal 2x2 matrix and therefore reduce the number of my unknowns. Okay, so this is what I've written down here. So we only have to look at the diagonal terms. And now, of course, we can sort of repeat, the same kind of argument. Well, I put here this reference. I mean, maybe that's sort of not exactly precise, but anyway, they were looking already sort of also at the scaling problems for the one-component system. Now you can just copy, what they were trying to say, and you find, indeed, because the structure of the equation doesn't have changed so much, you find indeed this 1-to-3 scaling. And from this, as before, I mean, I assumed that the static correlator is short range. I mean, this gives me a static component, which is sort of, okay, it's just a question of counting. I mean, so maybe I should explain this. So you see, we're talking about the static component, which is equal to 1/2, and this means basically that when I look at the dh of x, which is my phi, I think I've switched already to the phi variables. Yeah, maybe I didn't emphasize enough. I mean, so here I'm looking at the phi variables, and so what I mean by 1/2 is that the phi is uncorrelated. I mean, has a finite correlation length. So on a large scale, the phi will look like white noise, right? I mean, if I coarse-grain the system, and if I look at larger distances, because I have a finite correlation length, then on that scale it will look like white noise already. Okay, and so this is what I've written down here. And then when you do this rescaling argument, I mean, then you find that this sum is equal to 2, and therefore you find the dynamic exponents we have. That's exactly the same as for the one-component case. And again, I mean, you should maybe be a little bit suspicious, whether this is actually the correct story, because, it's naive power counting and not more. Okay. So now I want to sort of explain for you what are these what mean by the universality classes. I mean, so I take these two diagonal components. I mean, maybe if I'm very careful, maybe I should not put 2/3, but maybe some other factor. It wouldn't change my argument at all. I mean, and so in the simulations we see the 2/3. I mean, with fairly high precision. So let me just sort of leave it like it is. And this one comes because, I mean, the S of alpha x, I mean, this correlator, because it's a stochastic conservation law, when I take the integral over dx, I mean, it has to be independent of time. I mean, therefore, this is a dx volume element, so I have to put a 1/t3 in front. And then there's some yet unknown function, and then it must be an argument of t to the 2/3. I mean, that's just like for the one-component case, but now I assume that this kind of scaling holds for both components. And now, what does it mean for two control parameters to be in the same universality class? Well, I mean, that's pretty obvious. You see, I take some bare parameter x and y, and then I take another set of bare parameters which I called x tilde and y tilde. And then I do the long time limit, and then I'm, finding out what kind of correlation function do I see. So I will see some g for the xy, and I will see some x tilde and y tilde I will see some g tilde for the x, y tilde and x for x tilde and y tilde. Okay. So in which case are they in the same universality class? Well, you see, now we have two components. I mean, so basically what we're saying is you could do a dilation of this two vector, or you could sort of do a rotation. Now in our case, you see, we somehow fixed one coordinate already, because I'm saying that this little 2 by 2 matrix is already diagonal, and I don't want to sort of, I don't want to bother with this. So the rotations are ruled out. But in general, of course, the idea that I have to sort of, also, it's equivalent. If I take, if I take this little 2 by 2 correlator matrix, and if I rotate it, and dilate it, we would say it's in the same class, right? It's sort of a trivial change of that scaling function. And therefore, but the rotation goes out, and so in our case, it's just sort of a dilation. So I can just sort of dilate component 1 and dilate component 2, and if this two g's are related by dilation, then I would say it's in the same universality class. Okay. Or the other possibility is that that these are just two different functions. Maybe they look similar, they have a similar fake, but there's no simple relation between these two functions, and then I would say that they are in two different universality classes. And so the question which I would like to answer is what is happening here? Okay? I have two parameters. So it could be that every xy is sort of its own universality class by itself, right? Or whatever. This is sort of what I would try to find out and sort of try to explain. All right. So now I have to sort of put a few let's see, how much time do I have? Not too much, right?
30 minutes. I think we started 4 minutes late. So
okay, all right, okay. So there are sort of few things which are not sort of important, but I think the main thing is really that you understand what is this issue of universality. Okay, so one thing is one question about what parameters of x and y I can allow. And there's sort of an argument which is called hyperbolic stability. And what turns out, actually, when you look at these control parameters, if the product is positive, so if I'm looking at the one quadrant or the three quadrant, here everything seems to be okay, and you would expect to have a nice steady state with a finite correlation length. However, and this is something which was discovered already numerically by Kadar, but this sort of stability sort of underlines this property, is that when I look at the quadrant 2 and 4, then the solution seems to be unstable. And it's not a difficult argument, and so the physics in these two things, when you look in the Weinberger paper, he discusses also this unstable region and what he thinks is actually happening, but it's sort of outside of the kind of things which I want to do. So the universality classes are now the question sort of, let's forget about this, the negative one. That's sort of the same. Basically, I'm looking here at the positive quadrant, and I want to understand the universality class in that quadrant. Yes?
Can you have another situation when the system is classically unstable, but fluctuations actually make it stable?
Of course, such phenomena could be happening. I understand that, but this is exponential instability, and so it's unlikely that diffusion and noise would stabilize that. You see also from the there's something else happening, right? Okay, so then I want to sort of start from some work which we did a few years ago, where we looked at the simplification, where okay, so maybe I should go back. maybe I just want to go back to the equation. Okay, so here, we look at the special case where x is equal to y. So this is sort of, maybe I should put up our phase diagram, what we are learning step by step. Oh, you cannot see this. Okay, so anyway, so I put it down here again. I mean, so here's my x and here's my y. And now I'm discussing what happens along the diagonal, right? So this one, okay? And now on the diagonal, find the so you should look here. I mean, so I'm looking now at the diagonal, and if I look exactly at x and y equal to 1, I mean, so I'm looking at 1 here somewhere 1, I mean, at this point, then what you find is that you can just sort of do a simple rotation by 45 degrees, and then you get decoupled equations, right? I mean, everything, when it's a simple linear transformation of the whole situation, and if I put these coefficients in this particular way, I mean, then it decouples, and so that's of course a trivial case. So at that point, I mean, we know everything, right? I mean, because it's just decoupled. But now, as we go away from the special point x equal y equal 1, I mean, then of course something else happened, and what we found in earlier sort of work is that now we have sort of these scaling functions which depend now on x, y, but x is equal to y, so they depend only on x, and we find that in fact these scaling functions do depend smoothly on x, right? And I cannot sort of relate them by any kind of simple dilation transformation, and you also see that the two functions have different heights, and anyway, so the conclusion from that work was that when I look along the diagonal, every point is its own universality class. These are different universality classes. As I go along this line, every point in this line will belong to a different universality class. Okay. All right. So now the question is, what happens if we go a little bit? Okay, so here's sort of one picture so that you can see, I mean, this is, for instance, for x equal y equals infinity, and you see that, they look different like what you would see for the scaling function for the one component system, and, it cannot be related to any kind of, by any kind of simple transformation to the KPZ function. Okay, so now I want to explain one case which is called the Kohl-Hopf line. Okay, so which is line? This line over here. I mean, this is one. Here was a special point, and now we're looking at this line. And I'm trying to argue that these points belong all to the same universality class. And it's the universality class which corresponds to the case where the two components are actually decoupled. Right? Okay, so let me see how this argument works. So let's see. I mean, so first we do sort of like linear transformation up here, which is so I'm now looking at x equal to 1. And I'm varying the y. And now you do a simple linear transformation, I mean, which, okay. So just do this transformation, and then you do what people call after I have done this, I mean, you do the Kohl-Hopf transformation, which is simply looking at the exponential of h, and that sort of linearizes the system into a system which looks like much simpler because, it's not linear in this, what people call the partition function or whatever the Kohl-Hopf transform. So it's C alpha is just all the diffusion equation. So that is very simple. And then there's a term which is linear in C alpha. That's also simple, but it's modified with, it's multiplied by a potential, which is now our noise potential, which is, of course, some random function in x and t. So, basically you have to solve, Schrödinger type of equation or heat equation in the presence of a space-time random noise. And so if you can do this, everything is fine, and then you see the two decoupled equations. But when you do this computation very carefully, then you realize that this noise is no longer, I have two components, and the two components are no longer independent. Okay? And so, here I've written down for you sort of what is precisely the noise. You see that, it sort of has this particular form. This is the diagonal, that's the off-diagonal, and then you see that I have this off-diagonal piece, which is zero only in the case where y is equal to 1. So then we are back to what we know already, but now I have a situation where y is different from 1. But then, there's this simple argument that, when you look at this thing, it's multiplied by x and xy and pt prime. So this kind of correlation comes into effect only if sort of these directed polymers to which you can map it are actually sort of, okay, so it only comes sort of when you have an overlap of the polymers, which, okay, so I've written down here sort of the equation for how you write it in terms of directed polymers. And the main point, the main message is that it will be dependent only if these directed polymer cross, and these crossings are sort of subdominant compared to the linear, on the long time scale which we are looking. And so you would argue that when I look for very long times, eventually it will just go to two independent polymers, and that means that I'm eventually sort of in the long time limit, maybe I'm starting over here as per parameter, but in the long time limit, I will actually end up on the point 1, 1 on the diagonal. Okay, so that's one case where you can see that, now what I have argued that this line is one single universality class. Okay, now I would like to argue, this I will do very quickly, I want to argue that if I go away from the Kohl-Hopf line, I go to somewhat more general, and this diagram maybe to some point over here, exactly something similar will be happening. Okay, so because of time, I will not sort of go into this in any more detail. Maybe I should just sort of give you the key idea of what we are doing here. So now, we have the situation that your static correlator is not exactly delta correlated. But now, this is on the lattice scale. So, it's just on a very fine scale. And so I do a little bit of coarse graining. If I do the coarse graining, then I will see again the white noise. And so then I just rework my coupled equations under this kind of coarse graining. And what I find is a new KPZ equation with new coefficients, but with this additional information that the static state must be the steady state must be white noise. But it's sort of one not so deep sort of assertion that which you can prove quite easily, that if the steady state is white noise, you must be on this diagonal line. If I'm away, then it will be just a different state. I don't know what it is, but it will not be the uncorrelated state which I know after coarse graining must be present. And therefore, the argument is that, so here you see maybe this is on the next line. Yeah, you see these are the transformed equation. But the additional information which I have is that the steady state is actually white noise, and therefore, the claim is that whenever I look somewhere up here, the x coordinate stays fixed, and the final thing which I'm going to see here, the universality class to which I'm flowing, is actually the one sitting on the diagonal.
Sorry, you drew it as a straight line, but couldn't it just be a curve that is the axis?
Well, I think from the argument, when you have to go through the argument. I mean, yeah, you're completely correct. I mean, a priori you might think it should be might be curved, right? But from the argument which we've given, if you do the computation, we actually find it's a straight line.
Again, the line is call off. The line is the call off line or the
No.
Or the
So what I'm saying is, this is the line x equal to 1, where I can use sort of this call-off transformation to argue that I'm going to 1, 1. And if I'm going your way, I mean, then, okay.
But you're sure that you always go on the, I mean.
Well, I mean, if you do the transformation, you see that I have this equation at the end, and the x argument hasn't changed at all, right? And I'm just looking at the y, and if I want to satisfy this equation, then I have to put these terms. I mean, I have to put this term equal to this term, right? Okay, so now let's see. Okay, so this is again the same picture which I showed you already, and now I want to sort of let's see. Yeah, so I want to show you some sort of okay. So this is now an argument about the universality classes, but if I mean, it's a rough argument, and the only way how we can actually sort of see whether we made maybe some approximation which are unjustified or things which are overlooked. In any case, I mean, in order to see this, I mean, you have to run some Monte Carlo simulations, and the simulations which we did was sort of one is sort of on the Kohl-Hopf line, and we have another set of data which is sort of on the point where x is equal to, and we are sitting on this line here, right? Okay, so let me just show you the picture. I mean, they're not so terribly informative. I guess the main point which I would like to emphasize is that you look at the static correlator. This is exactly x equal 1, y equal 1, where the two components are independent. And of course, the static correlator must be in delta. But when I go away, I mean, then you see that the static correlator is sort of, it broadens a little bit. I mean, not very much, but it broadens a little bit. And then, our theory sort of, tells you what should be happening. And you see that we scaled here everything in terms of t to the 2 thirds, okay? So let me just sort of, that's another set for the point for 2. I mean, it's the same sort of, same features, and of course, these curves look a little bit different, but you have to look at them for a while, I mean, to find them interesting, and so, and here we sort of do now the scaling plot. I mean, we have here the one component, we have the 2 component. This is the x equal to 2, and we have 3 different values of y, and they sort of seem to lie sort of, at least sort of within this kind of approximation, they seem to lie sort of on a good, of course there's noise, but at least sort of qualitatively, we would say that, sort of, it scales in the way how we expected.
So you think that the spread comes from the noise time, or that we can reduce it maybe by offsetting time?
No, how was that?
In my talk, I was presenting like offsetting time by constant phenomenon,
Ah,
right?
I'm not sure. Maybe we can discuss it.
This is an equilibrium, I think. So there's no, so it's like time difference, right? It's not like there's no argument.
Time difference in current. Oh, okay, yeah.
Equilibrium.
Yeah, okay, no, then I agree. Yeah.
Okay, so now I want to. I mean, this is not well. I mean, I still have 2 minutes. I mean, so I want to tell you one new result, which is sort of well, maybe I can do it over here. So this is Schmidt and Company, and they simulated now a different model. I mean, which should be in the same class. So you have here a lane 1, and you have a lane 2, and here you do TASEP. I mean, so you jump always this way if there's an empty side, right? I mean, maybe here, and then one is sort of here. Okay. Now. And then downstairs, so you do the same thing, right? I mean, so particles are sitting over here, and they would only go this way, right? I mean, you jump only if the side you want to jump to is actually empty. Okay? This is something which in the literature is called HASEP. All right, and then you know, if at half filling, I mean, it satisfies all the conditions, and so in half filling, you know, it would, in a continuum limit, it would be described by one of the equations which I showed you. But in fact, in the continuum limit, I mean, you know, the parameters of this model are sitting exactly along this line here, right? I mean, so it will be always what we call cyclic. I mean, you will always have this different product measure. And so they plot now. So here you have the parameter, which I guess is sort of our x here, right? I mean, so here is x equal to 1, and here they have here they plot what is the c, which we guessed is v over 2, right? I mean, this was our dynamical exponent, right? Okay. Okay, so you know, this was our prediction. Now, at 1, of course, you know, they find exactly the same thing. But then when they look more carefully and look at the scaling exponents for larger x, then you know, they say it's a curve which looks like this. Okay? So this is maybe 2, and this is 1.
Sorry, why the two curves?
Hmm?
Why the two curves?
Well, I mean, we have two dynamical scaling exponents. No?
Two modes.
Oh, I see. So the two modes have different scaling.
Okay, so you're doing this model. I mean, you know, it just falls exactly into this glass, and then the question, what they ask is, you know, they measured exactly the same correlation functions, and with their data, I mean, they fitted what would be the dynamical scaling exponent. And they find, we predicted 3 over 2, right? I mean, this was the whole talk. But they do not find c over 2, but they find sort of a deviation here, right? And so you know, the deviation is something like 1.6 here, and then maybe, you know, at the largest value, and 1.4 over here. It's not dramatic, but it's clearly different. Okay.
But, I mean, are corrections to scaling understood? So from your picture, you know, it looks like in the language of RG, you would say there's maybe an exactly marginal direction and an irrelevant direction.
Yeah, that's right, yeah.
So the irrelevant direction would lead to a correction to scaling. Is that exponent? Do you know that exponent? And would it?
I don't think we know that exponent. Yeah.
Okay, because that could explain.
Because you see, we never do any proper RG, right?
Yeah. But they're confident they're seeing. They're not.
Well, I mean, this is simply a numerical evidence,
yeah.
but you know, I did not display the pictures, but you know, it is a very high quality. I mean, it looks sort of, you know, they look. I mean, they are not in disagreement what we are saying. The point is that they're just arguing that we looked at too short a time. You see, they're doing effect of, you know, they do effect of 10 longer times than what we did. And then they argue that then you will see, you know, sort of, I mean, at a shorter time, of course, you know, things are still sort of not so well developed, and you see sort of still the old one, but at longer times you really see the sort of, and anyway, I mean, I can show you the picture that you see that it's actually, it looks to me actually quite convincing. Okay? And so here's sort of, you know, the conclusion of my talk is that, you know, in order to sort of understand, you know, what's actually really going on is that we have to do some more serious RG type of computations. Now, Weinberger and Kadar did one loop, and one loop gives you the 3 over 2. And one loop gives you also this particular, you know, when you look at the fixed points, I mean, they're lying on the diagonal. So on one loop, I mean, everything is sort of okay, right? Now, 2 loop seems to be somewhat demanding point. Personally, I would not really advise 2. I mean, see, what I really would like to see is that if somebody would, you know, sort of repeat, you know, the functional RG of Carnet et al., which you know, in the single component system gives results which are almost exactly close to the exact solution, and therefore, you know, I think this would be the method in order to clarify what's going on. Okay, so thank you very much.
Time for questions, yeah.
Does anything simplify if you take x to 0 or infinity? It seems like those also seem like potentially tractable limits.
What was that?
If you take x to 0 or x to infinity,
Well,
like this origin
okay.
or...
I mean, x to 0, well, no, the x down here, at least numerically, it looks pretty singular, right? I mean, because I mean, you know, the point 0 in this coordinate system is I mean, it's really a singularity, right? I mean, so now we actually, you know, in the first paper, we actually sort of, without sort of knowing in some sense, I mean, we look at the case x equal to infinity, right? And x equal to infinity was sort of, you know, where you see, you know, the strongest deviations from the decoupled case, right? And so in the TARSET simulation, basically means that you know, if the jump rate is 1, I mean, then the way how they modify one jump rate is, you know, decreasing this to 1/4. I mean, so the TARSET, this corresponds to the x equal infinity limit. So for the TARSET, the x equal infinity limit is extremely well accessible. And you know, when I say 1.6 and 1.4, this is actually already at x equal infinity. Mm-hmm.
And so is the stationary measures there still the infinite temperature measure, or is it something else?
No, the stationary, so for the TARSET model, the stationary is still a product, right? I mean, so it's still sort of uncorrelated, right? And also, you know, I mean, okay, we have not maybe simulated, yeah, if you go for a little bit of, okay, we only have the data which I showed you, right? I mean, so, I mean, if I go not too far away from the diagonal, I mean, it looks rather reasonable that it should, and you see the decay is extremely quickly, right? It's not even exponential decay. I mean, numerically it's sort of, you know, 0 after 4, and that is also so.
Questions?
Sorry, I couldn't fully follow the derivation of this equation in the limit of xy goes to infinity. Does it involve some rescaling of space or time?
What are you looking at? You're looking at this one here?
Yeah, so starting from original equation xy.
Okay, well, okay, I basically I just repeated what I'm trying to say. I mean, so if we, so first we argue that you know, on a slightly larger scale, the steady state looks like Gaussian white noise is two independent components. And then here we do a spatial sort of coarse graining, and then the claim is that, you know, after the coarse graining step, you know, the coarse grained KPZ equation will look like this. I mean, with a kappa which is given sort of, I mean, the C1 and C2 are the two components of the static correlator. So maybe I was a little bit short about, maybe I can explain you afterwards. I was a little bit short about this argument, yeah.
But in the original equation for H, you had x and y, which goes to infinity.
Yeah,
so
I mean,
you need a rescaling of space or time?
Okay, this particular equation is sort of this x equal y to infinity, right? I mean, so the kappa is actually the ratio of these two systems. I can